February 22nd was a monumental day for America when, after 50 years, an American spacecraft successfully attempted a landing on the lunar surface. The Intuitive Machines Chandra lander made an attempt at touchdown on the lunar South Pole. This was significant because it marked America's return to the moon for the first time since 1972, and it was being done through a private company's mission. Initially, the company reported it as a successful and honest landing. However, as updates came in, it surprised everyone. We've learned that as it made its final descent, one of the legs of the Chandra lander became lodged in a hole on the lunar surface. This resulted in the entire spacecraft tilting to one side. Furthermore, it currently sits in this tilted position. It is in a tilted position with some solar panels sideways instead of upright, attempting to gather energy. Despite the unexpected setback, both the teams at Intuitive Machines and NASA remain optimistic that the spacecraft can successfully carry out its scientific mission. Now, let's explore the details of the landing, how it unfolded, the implications for the remaining mission, and many more intriguing aspects. Let us know about it in detail in today's episode of Cosmic Discovery. On the 22nd, as the lander approached the moon's orbit, a few challenges cropped up. Initially, the team reported issues with Odysseus's laser rangefinders, crucial for determining altitude and horizontal velocity. To tackle this, they had to improvise, turning to an experimental NASA instrument carried by Odysseus. It wasn't the original plan, but they made it work well enough for the lander to touch down on the moon intact. During the landing, there was uncertainty among the teams about whether the lander had successfully made contact with the lunar surface. Inside the control room, team members were scrutinizing monitors and reviewing lander data. Eventually, they confirmed the successful touchdown. The company even took to Twitter, announcing that the lander was upright and had commenced sending data, overcoming the unexpected hurdles along the way. It wasn't until yesterday, on the 23rd, during a NASA briefing, that we got a clearer picture of what happened to the lander. Contrary to earlier reports, the lander wasn't in an upright position. Instead, it had tipped over on its side. The CEO of Intuitive Machines explained, "We think we descended at about 6 meters per hour vertically and 2 meters per hour sideways, likening it to walking speed. We caught a foot in the surface, causing the lander to tip. Sunlight is reaching us from the side, and we believe we have solar exposure on the top deck. Most of our payloads are visible, and we are actively gathering scientific data," he reassured. To put it differently, it's speculated that one of the 6 main landing legs of the lander got stuck while it was still slightly moving sideways, causing it to tip over. The lander, standing tall at 4.6 meters and with a diameter of 1.6 meters, was originally designed for a straight vertical descent without any lateral motion. Additionally, during the press conference, the CEO of Intuitive Machines used a toy model of the lander to illustrate his understanding of the situation. He pointed out that the blue object in the model, representing a rock, is believed to be the point of contact, with the top of the spacecraft landing on it, creating a somewhat level surface. Regarding the initial announcement that the lander was upright shortly after landing, the CEO provided some clarification. He explained, "Yesterday we believed we were in an upright position because the tanks were registering lunar gravity and fill levels with residuals in the X direction." He continued, "However, this was still based on telemetry. It was only after working through the night to obtain additional telemetry in the Z direction that we observed the residual tank quantities. This information gives us a more certain understanding of the vehicle's orientation." As for the visual documentation of the incident, the currently available images are limited to a pre-landing snapshot. Specifically, it's a photograph taken 125 meters or 200 kilometers uprange from the intended landing site at an altitude of approximately 6 meters or 10 kilometers. Unfortunately, one of the primary methods planned for capturing the landing attempt on camera is no longer viable. In this situation, the lander was equipped with the Eagle Cam, a device crafted by students at Embry-Riddle Aeronautical University, ER. The Eagle Cam was designed to deploy from Otis at a height of about 100 feet or 30 meters above the lunar surface to capture images of the craft's touchdown from below. However, due to the navigation challenges I mentioned earlier, which necessitated the uplink of a software patch, the decision was taken to power down EagleCam during the landing and refrain from deploying it during Odysseus' final descent, according to the Director of News and Media Relations at ER. He went on to explain, "Nevertheless, both the Intuitive Machines and EagleCam teams have intentions to activate EagleCam and capture visuals of the lander on the lunar surface as the mission progresses. The lander is equipped with alternative cameras, and during the recent briefing, the CEO of IM expressed their hope to obtain some images over the weekend and share them. At the moment, we don't have much to showcase." Given this recent development, the pressing question emerges. What implications does the lander's sideways position have on the remainder of the mission? During the Q&A session at the conclusion of the briefing, there was an inquiry about how the altered orientation would impact the ongoing mission. The CEO addressed this concern, stating, "As I mentioned earlier, we don't have any active payloads on Panel E, which, to my understanding, is facing the moon. Fortunately, the active payloads requiring communication and command are all exposed to the outer environment. However, we do have antennas directed towards the lunar surface, rendering them ineffective for transmitting data to Earth. This poses a significant limitation on our ability to communicate and retrieve essential mission data. This is the most compromised aspect," he emphasized. Actually, the lone payload situated on Panel E, facing the moon, is a stationary one, an art piece contributed by an artist, or so the company currently believes, acknowledging there are still certain uncertainties. They further explained, "If a foot catches, it could potentially result in a gentle tipping over, potentially fracturing the landing gear. The lander seems to be resting on a rock, slightly elevated above the surface, judging by the power it's generating," he shared. "Alternatively, the foot might be in a crevice." Shifting our focus back to the future of the mission, he then highlighted, "As I mentioned earlier, the solar panel on the top deck was angled at about a 30-degree tilt upward before landing on the South Pole. Now that we've tipped over, the status of the solar panel's health is uncertain," he explained. "While there are other solar panels, they are no longer in an upright position, which is not the ideal scenario. Despite these challenges, they seem to be reasonably content with the outcome, even with the lander resting on its side." Taking a closer examination of all the payloads on board provides us with a clearer understanding of how they are impacted by the sideways landing. In total, there are 12 payloads, consisting of 6 from NASA and 6 commercial ones. The inaugural commercial payload comes from Columbia Sports, conducting trials on a specialized lining designed to withstand the harsh lunar conditions. This lining is specifically applied to certain panels, potentially offering valuable insights both before and after the landing. Following this is the previously mentioned EagleCam. Although the original plan was to deploy it during the descent, the current position of the lander, despite the intent to still deploy it, may pose challenges to this process. The feasibility of deployment depends on the specific side of the lander where the cam is located and whether the team still deems it suitable for deployment. Following that is the art segment, featuring several sculptures known as moon faces. Subsequently, there is ILOX, equipped with a miniaturized dual-camera lunar imaging suite, comprising one wide field and one narrow field camera. The primary objective was to aim and capture some of the initial images of the Milky Way galaxy center from the moon's surface, along with engaging in other celestial astronomy activities. While the sideways landing may pose some challenges, the camera is likely still capable of capturing images of its original targets. The last 2 commercial payloads involve a secure lunar repository and a data center, both of which should remain unaffected by the landing, unless certain antennas are obstructed. Regarding the NASA payloads, we then have the RFMG, Radio Frequency Mass Gauge. This utilizes radio waves and antennas in the Nova tank to precisely measure the amount of available propellant. This technology has been in operation, collecting data even before the actual landing. Following that is LN1, Lunar Node 1 Navigation Demonstrator. This scientific instrument functioned daily throughout the cruise phase, and as the landing date approached, the radio beacon played a crucial role in supporting accurate geolocation and navigation observations for orbiters, landers, and surface personnel. It digitally confirmed their positions on the Moon concerning other crafts, ground stations, or rovers in motion. Essentially, a significant part of its mission has already been successfully accomplished. Additionally, there's SCALES, stereo cameras for lunar plume surface studies. This experiment aimed to capture images of the lander's engine plume interacting with the lunar surface as LSUS descended and as the dust plumes settled around the spacecraft. Another component is the Navigation Doppler LiDAR for Precise Velocity and Ranging Sensing, or NDL. Its primary function was to measure the distance from the ground during descent, a task already accomplished. Moving on, we have the Laser Retroreflector Array, or LLRA. This assembly comprises 8 approximately 1-inch retroreflectors, unique mirrors utilized for distance measurement, attached to the lander. If IM's assessment of the lander's orientation and panel E facing the Moon is correct, this experiment could still offer valuable information as it remains exposed. Lastly, there's ROSIS, radio observations of the lunar surface photoelectron sheath. This technology aims to measure the electron plasma environment on the lunar surface, among other functions, and we anticipate receiving more details about its actions in the coming days. As per Intuitive Machines, the lander wasn't designed to endure the lunar night and relies on sunlight for its solar panels to power its operations. To provide context, a complete lunar day spans 28.3 Earth days, with 14.15 Earth days of sunlight and an equal duration of darkness. Since the LER landed on the Moon around what could be termed lunar noon, approximately 7 Earth days after the lunar sunrise, the lander will have approximately 5 remaining Earth days of sunlight for the remainder of that lunar day before the next lunar sunset. Consequently, the Odysseus system has been programmed to fully and definitively shut down after 7 days, marking the conclusion of the lunar day once the sun sets over the landing site. Considering this, regardless of the lander's current state, it has a finite amount of time remaining. It appears that the Odysseus lander is not in an upright position, but is, in fact, tipped over. This is less than ideal, and in the upcoming days, we will gain further insights into its condition and how it influences the ongoing scientific mission. Observing its development and assessing the repercussions on the space industry will be crucial. Thank you sincerely for your attention.